Hello students, welcome to lecture 6 of our online chemistry classes. Last class we have solved some questions regarding the formula of the unit cell in different situations. We have covered almost all situations. Now I have given you one question as homework. Half question we have done together and some parts, 3 parts I have given you as homework. Let's see how you have done that. In part D, because A and B we have solved together, if all the atoms on one face are removed, so all the atoms on one face are removed. So how many A are removed? A are present at corners, and if one face is removed, 4 atoms are removed. 1, 2, 3, 4. So 8 minus 4. B, they are present as face center. This all B. So that also one get removed. 6 minus 1, 5. C is atoms present at edge center, and there are 4 edges. So these 4 atoms are get removed. So 12 minus 4, 8. And D is present in body center. There is no effect on number of B here. So it is 0, so it is 1. Contribution of corner is 1 by 8. Face center is 1 by 2. Edge center is 1 by 4. Body center is 1. So A, 1 by 2. 5 by 2. 8 by 4 is 2. 1 into 1 is 1. Multiplied by 2. This 2 to get cancelled. A1. 5 by 2 into 2 to get cancelled. B5. Multiply by 2, 2 into 2, 4. And D1 into 2 is 2. So A, B5, C4 and D2 is correct formula. For this situation when all the atoms along the phase diagonals are removed. So phase diagonal, which is the phase diagonal here. The phase diagonal is this one, which runs through phase. There are 2 atoms, these 2 on corner and 1 from the phase center. There is no atom removed from edge center here. They are remain as it is, and there is no removal of body center atom. So 8 minus 2, 6, 6 minus 1, 5, 12 minus 0, 12, 1 minus 0, 1. 6 into 1 by 8, 3 by 4, 5 into 1 by 2, 5 by 2, 12 into 1 by 4 is 3, D1 into 1 is 1, multiply by 3, multiply by 4, 3 into 3 by 4 into 4, 4, 4 get cancelled, 3, 4, 5 into 2 is 10, 4, 12, 1 into 4 is 4. And the last one, we have to remove that to the body diagonal, which runs through this part to this part. It starts with this and ends here. This is body diagonal. There are 2 atoms at the corner which get removed, and there is no edge center or face center, or there is a one atom which is removed from, yes, here it is 1 minus 1 from the body center. D is get removed. That's why 1 minus 1 is 0, 12 minus 0 is 12, 6 minus 0 is 6, 8 minus 2 is 6, 6 into 1 by 8, 3 by 4, B 6 into 1 by 2, 3, C 12 into 1 by 4, 3, D 0 into 1 is 0, multiply by 4, 3, 12, 12. A, again simplify, divide by 3, 1, divide by 3, 4, divide by 3, 4. A, B4, C4 is the formula. So you try to understand these examples so that your all concepts will be clear. Now next part which we have to learn is the coordination number. So we'll see that definition of coordination number, because in a unit cell this coordination number is very important concept. So I will write the definition and we will try to understand it. So coordination number we can say number of particles. It is nothing but it is a number of what? Number of particles immediately adjacent means neighbor, adjacent, number of particles immediately adjacent to each particle in a crystal. In a crystal means in a unit cell, because crystal is nothing but repetition of the unit cell. So it is a number. Coordination number is a number. Number of what? Particles. But which particles? Which are immediately adjacent to every particle. It's called as the coordination number. Very important definition. Many times it has been asked for 1 mark. Define coordination number. It is the number of particles immediately adjacent to each particle. It's called as the coordination number. Now I will define the coordination number in simple cubic unit cell, body centered cubic unit cell, and face centered cubic unit cell, because these are the unit cells which are there in our syllabus. So we try to understand that. I will draw the diagram of simple cubic unit cell where particles are present only at corners. They are present only at corners. They are present only at corners. These are the particles which are present only at corners, like this. And if you want to know coordination number of this particle, we can easily consider this particle and say that this is immediately adjacent to this particle. So 1. For this particle, again the nearest particle is this one. This is 2, and this is 3 of the same unit cell. But we can imagine that this 3-dimensional structure. So there is a unit cell which is beside this, like this one. So there is one more particle here. There is one more unit cell which is outside to this unit cell. So one more particle is here. And there is one more unit cell which is near to this. I will explain this. And there is one more. So this particle in a simple cubic unit cell which is at corner is surrounded by 1, 2, 3, 4, 5 and 6 particles. That's why the coordination number is equal to 6 for simple, or another name we give it to this type of cell is primitive cubic unit cell. So many times question has been asked, what is the coordination number of simple or primitive cubic unit cell? We should say that coordination number is 6. That's how we are calculating. 3 from this 1, 2, 3. One is beside this 4. One is above it 5. One is backside this 6. In that way. Now what about the body centered cubic unit cell? We know what we mean by body centered cubic unit cell. These are the type of unit cells where particles are present along with corners, they are present at body center. So this is 1, 2, 3, 4, 5, 6, 7, 8 are at corners, and one particle which is present in the body center. We can say that this particle is surrounded by this which is present in this body center. It's surrounded by immediately adjacent particles. So this particle is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. That's why we can say that coordination number of this particular unit cell is 8, and this is for body center cubic units. So BCC has coordination number equals to 8. Now consider the face centered cubic unit cell. This is the cube. Once again I am drawing it. Try to understand this. Slight imagination is needed. I already told you, but not at all difficult. These particles are present at corners. These particles are present at corners, and the particles are present in face center also, like this. Like this. There are 6 faces, and it is surrounded by the 6 faces. They have one particle at face center. Now consider this particle for which we are calculating the coordination number. This is in directly contact with 1, 2, 3, 4 of the same plane, as well as it is in contact with these particles also of the plane which is below it. So this is 4 and this is 4, and there is one more unit cell above it. So that also 4. Yes, you are understanding, because this part is repeated here, and then this part will come, right? So we can say that 4 in the same plane, 4 in below plane, and 4 in above plane. That's why the coordination number is 12 for face centered cubic unit cell. Coordination number is 12. So for simple or primitive cubic unit cell it is 6. For body centered cubic unit cell it is 8, and for face centered cubic unit cell it is 12. So this is the definition of coordination number, and number of that coordination number in these 3 types of the different unit cells. Now we can go further and we can calculate about the arrangement. We call it as close packing. In the crystal system. So this is very important part. Try to understand this. Many students get confused in understanding of this part. What we are learning now is close packed structures. Close packed structures. Now why structures are close packed? We know that particles, we are assuming them as rigid, incompressible spheres, and there is interparticle force. What are the example of interparticle force? It may be London dispersion force, It may be dipole-dipole interaction, it may be hydrogen bonding, it may be metallic bonding, it may be ionic bonding, or it may be covalent bonding, depending on which particles we are talking about. Due to this interparticle force, particles are close packed. They are very close to one another because of this force of attraction. And that's why it gives stability. It gives stability to the particular crystal system. Now we have to arrange these particles in various dimensions. First is we have to learn close packing in one dimension. One dimension. Close packing one dimension. In close packing of one dimension, we'll arrange the particles side by side like this one. This is one particle. This is another particle. They are side by side. These particles are arranged. You can also draw this diagram with the 2 rupee coin, because that will be perfectly sphere. I have brought this on rent from my wife. It looks, the size is sufficient, I think, right? So, if we look at this particular part, this particular sphere, how many immediately existing particles are there? We can say this 1 and this 2. So we can say that coordination number in this one dimension is 2 here, because it is in contact. This sphere is in contact with this 2 sphere. This sphere also in contact with 2 sphere. So in one dimension, coordination number equals to 2. Now close packing in 2 dimensions. There is nothing difficult into it. So you can say close packing in 2 dimensions. There are 2 ways of arranging this particle in a 2 dimension. See what is the way. First way is like this one. It will take some time, but we should spend that time in drawing, because then only we will have clear understanding regarding this. Like this, one above another. Particles are arranged. Like this. So, if we consider this particle, it is in immediate contact with these 4 particles, like this. And that's why coordination number is equal to 4, and this is called as square closed pattern. And what is the arrangement? If this is layer A, this is exactly identical. So this also A. This is also exactly identical. It is also A, like that. Same type of particles are avoided. This is one way of arranging it. We call it as A type. B type is like this one. I will change this only. This one dimension already we have learned. So I will just arrange this because already I have drawn this 5 spheres. I don't want to waste time on drawing this sphere. This is B. Now what is the B arrangement? B arrangement is we have to arrange another spheres in this space like this. Like this. Yes, it will take some time, but have patience. You also draw once you know how to draw it. If you draw, you will not get bored. Otherwise, just to see others drawing this diagram, you may feel very bored. So, with 2 rupees coin on the paper, you can draw it. Another one is in this depression. This space is created. You can see the difference. 3 layers will form not much meaning. On paper it will be very nice to draw this diagram because you will have better control on it. Because coin is also smaller and paper is also smaller, so it does not require much effort on paper, but it requires more effort on the board. So this is, you can see the difference. Difference is A, same alignment. Here difference is if it is A. We have our point clear. Otherwise, here one more. Right. If it is A, this is B. But it is not exactly like it. But third is like first one. So this is A, B, A type of arrangement we are getting. What is the coordination number? If we consider this particle, this is in immediate contact with this 1, 2, 3, 4, 5, 6. And if we connect all these 6 particles, their centers, because they are exactly the lattice points, what we get here is this type of diagram. And we can say that coordination number is 6, and this is called as the hexagonal closed pattern in 2 dimensions. And this type of void, this type of pattern space, see which space I am talking about, this space, it's called as triangular void, because it is like triangle. 2 types of voids are there, one pointing upward like this one, and another one which is pointing downward like this. two types of voids are present, and that voids, that vacant space, is called as triangular void. So this is in two dimensional. So the arrangement is A B A B A B, and the arrangement is A A A in the square closed pattern, and this is hexagonal closed pattern. Now we'll go for closed pattern in 3 dimensions, which actually exist and which is important for us. So closed pattern in 3 dimensions. I'll just rub these diagrams. They are there in textbook, in notes. You refer them and you draw at least 2-3 times. Then only you will understand how different arrangements are there and what are their coordination numbers, what they are exactly called. Now we have to deal with closed packing in 3 dimensions. Closed packing in 3 dimensions. Closed packing in 3 dimensions. In closed packing in 3 dimensions, the 3-4 types are there. First we will see this type. See carefully. One above A, we are talking about. Little delayed. If it's not perfect, you should excuse me. I am trying to draw as perfect as possible, but I don't want to spend much time also, because this is the easiest thing. To draw a circle with the help of this type of device, right? Yes, one more. One layer is arranged over the slides. Now we have this lattice point here. These are also spheres which are behind. 3-dimensionally we have packaged. See, if we connect this, what type of diagram? Kind of cube is created like this. So this is called as primitive cubic shape. This leads to primitive cubic unit cell, and the packing efficiency of this particular packing efficiency means how much space is occupied. Packing efficiency is 52.4%, means remaining 48.6 is vacant. The example is polonium in this case, and arrangement is A. It's exactly on the alignment, same alignment we are arranging the particles. So this is one way of arranging it. Now another way of arrangement in 3 dimensions. That will have one layer first, arrange here. I told you it will take some time. If you don't want to see it in detail, you can forward it. Isn't it? That option is with you. When you are in classroom, you cannot forward. But on YouTube you can forward me, right? So this is B and this is B layers I will draw. Like to till now it is 2 dimensions. Yes. Now we have 2 types of voids, 2 types of empty space. This upward triangle, downward triangle. We can keep another layer either on upward or on the downward. You understand this? We cannot keep on both ways. Either upward is covered, upward void is covered, or downward void is covered. We cannot have both in simultaneously. Then it will not be aligned properly. So what I will do? I will write the next layer on this upward type of void. This is second layer. I am adding. Here is upward, another upward. On that I am keeping another layer. So what I have done, I have kept the second layer on those vacancies, those voids which are having this upward triangle. Now once we do that, we have again 2 types of voids. One is, you can see carefully, or I will draw one more square so that we can easily distinguish it. Right here. Now first thing is, this is first layer. This is first layer and this is second layer. On that space you have kept the second sphere. Now we have two types of empty spaces. One with this where only 4 spheres are involved. White, grey and one this what type of color? Pista color, right side. So we call this as A. This is A. This is A. And another one, this one, where 3 white. This 1, 2, 3 white, and 3 this pista color 1, 2, 3. We call this as B type of white. Right. This is B, and this is A. Right. So A is the white which is covered by tetrahedral white, we call it. It takes some time, but I am just drawing this in front of you so that you can have idea. I have planned to draw it before class and then explain. But I thought that if I draw before you, you also have some thought of drawing. That's why I am drawing it. So this three white and one this second layer. This type of white, we call this as tetrahedral white. Tetrahedral. White means empty space. Why tetrahedral? Because 4 spheres are involved into it. So this A, this is A in our diagram, this small a. And another type of white which is present here is this type of white, where 3 white, 3A first layer and 3 second layer are involved. These 3 first layer and 3 second layer removed. And this type of white is called as octahedral white. Coordination number is 6 for this white and coordination number is 4. Tetra means 4 and octa means 6. Now if I keep this third sphere on this tetrahedral white, say this A, if I try to complete this A as the third layer, then what will happen? If I try to complete this white, here also A. If I cover this A here, then it is coinciding with this white, which is third layer. Isn't it? You are observing this. If I want to cover this A, then this layer C, third layer, is exactly identical to the first layer. Like this. And if I want to cover this B, which is tetrahedral, this is different than A first layer. It's not coinciding with the first layer. So depending on that, We have two types of arrangement. I will write here which type of arrangement we are talking about. Third layer is placed on. Third layer is placed on A or B. A is tetrahedroid and B is octahedroid. If third layer is placed on tetrahedroid, what type of arrangement we get? A, B, A, B, A, B, like that. And if it is placed on octahedroid, A, B, C, A, B, C type of arrangement we are getting. Just now we have seen. If we place third layer on this white, this is exactly identical to white one. And if we place here, it is not identical. So A, B, C if we place on B, and A, B, if we place on A. This type of arrangement, AB, we call it as hexagonal closed pattern. And this ABC, we call it as cubic closed packing or face centered cube is created out of that. The coordination number of FCC is same 12, and here CP, this is abbreviated as SCP, this is abbreviated as CCP, and this is abbreviated as FCC. So coordination number is same in these cases. And packing efficiency, which we will calculate, for this is 74% and for this also 74%. So packing efficiency is same, coordination number is same, arrangement is different. AB, HCP, ABC, and CCP or FCC. Another thing we can distinguish is about example. Example here are magnesium, manganese, zinc, vanadium and cadmium. And here examples are copper, silver, gold and platinum. Now how exactly this HCP and this FCC looks like? I will draw the diagram here. See those first diagram. You also try to draw those diagram. HCP is like graphite. You have seen that. This one plane. There is another plane. Here is third one. You want to just connect this point. Like this hexagon is there, and we have one more 3-layer particles. This is called as HCP. And look at the arrangement of particles. What type of arrangement we are talking about? This 1, 2, 3, 4, 5, 6. This particle is exactly above this one. They are exactly in alignment. So if this is layer A, this is layer B, and this is layer A. So it is A, B, A, B, A, B, like that. This is HCP, where element is A, B, A, B, A, B. Coordination number is 12, and packing efficiency is 74%. How the FCC looks like, you can draw that diagram also. Along with that, so look at the particles here, where they are present. So this is A, this is B, and this is not identical. This is not identical to this one. This is different, isn't it? So it is C, and this is A, and this is called as FCC. It is just like if I draw like this one, straight one, we don't observe like this. But if I slightly twist this way, you can see element A, B, C and A. So A, B, C, A, B, C is FCC or cubic closed packing, and A, B, A, B is HCP. How we got HCP? By keeping third layer on the tetrahedral void of second layer, and FCC on keeping the third layer on the octahedral void of the second layer. We are getting this type of pattern. So you read this and draw this diagram, then only you will have correct understanding regarding this. Practice of diagram is very much required, because then only you will have first hand information about how the pattern is there. Very simple part, revising once again, you will understand it. If you don't understand, I will solve it. So thank you for watching this video.